This research paper proposes a transparent and nonlinear method for variable selection in high-dimensional data. The authors argue that traditional approaches often fail to effectively identify and select complex nonlinear dependencies between predictors and response, leading to inaccurate predictions and poor model interpretability. To address this, they introduce a three-step heuristic search framework, dubbed Transparent and Nonlinear Variable Selection, TNVS, which categorizes input predictors into four non-overlapping subsets: relevant, uninformative, redundant, and conditionally independent. The TNVS method utilizes a nonlinear partial correlation coefficient to identify predictors with diverse complex nonlinear relevance to the response, including non-monotonic or oscillatory functional dependencies and interactions among predictors. Information entropy is employed to filter out uninformative predictors, Gram-Schmidt orthogonalization to remove redundant predictors, and nonlinear partial correlation to remove conditionally independent predictors. The authors highlight the importance of transparent information decoupling, which involves effectively selecting truly important predictors and transparently deleting predictors that are of no use for prediction. They argue that prevailing approaches often assume simple forms of functional dependencies and neglect the presence of uninformative predictors and multicollinearity in real-world applications. The proposed TNVS method is model-free, and the selected subset of predictors can be used as input for commonly used predictive models. Experimental results demonstrate the superior performance of the proposed method in terms of prediction accuracy and model interpretability compared to state-of-the-art baselines. The paper is organized into sections, with Section 2 reviewing related work, Section 3 describing concepts involved in information decoupling, Section 4 presenting the search framework of TNVS, and subsequent sections demonstrating the effectiveness and interpretability of the proposed method on simulation problems and real data applications. The authors conclude by highlighting the contributions of their method and discussing future work. In this research, we focus on improving feature screening methods by introducing a novel approach that incorporates nonlinear partial correlation coefficients. The study begins by highlighting the limitations of existing methods, particularly their inability to detect complex interactions and require prior knowledge of key variables. We then discuss the conditional dependence coefficient, CODEC, a nonlinear partial correlation coefficient that can measure the conditional dependence between variables. This coefficient is used to develop a forward selection method, feature ordering by conditional independence, foci, which, although efficient, has limitations in removing unimportant predictors during the search. Our approach addresses these limitations by introducing multiple time-saving measures to remove unimportant predictors and dividing the removed subset into quasi-chunks for better interpretability. This is achieved through information decoupling, where the input predictors are transparently grouped into four disjoint parts: relevant, uninformative, redundant, and conditionally independent subsets. The relevant subset is further defined, and its measure is described. The primary goal is to obtain the correlated subset from the input set. The conditional dependence coefficient is used to measure the nonlinear conditional correlation between the response and predictors, as well as the interaction between predictors in explaining the response. This approach is novel in its ability to handle complex nonlinear correlations and provide a fully interpretable method for variable selection. The proposed transparent and nonlinear variable selection (TNVS) approach is designed for high-dimensional data, aiming to separate candidate predictors into relevant, uninformative, redundant, and conditionally independent subsets. In the context of variable selection, it's crucial to identify and remove uninformative predictors that have little influence on the response variable, redundant predictors that are collinear with other predictors, and conditionally independent predictors that do not contribute to the model when given a subset of relevant predictors. To measure the relationship between a predictor and the response variable, the CODEC, conditional dependence coefficient, is utilized. The CODEC is a measure of the conditional dependence between two random vectors, and it can be used to identify uninformative, redundant, and conditionally independent predictors. For a predictor xj, its CODEC with the response variable y given the remaining predictors xg is denoted as Tn, y, xj, xg. If Tn, y, xj, xg is close to 0, xj can be considered an uninformative predictor. Shannon entropy is used to measure the uninformative predictors. Given a discrete predictor xj, its entropy h, xj, represents the expectation of the amount of information contained in the predictor. If h, xj, equals 0, xj is considered an uninformative predictor. For continuous predictors, data discretization is required beforehand. Gram-Schmidt orthogonalization, GSO, is applied to identify redundant predictors. If the variance of an orthogonal variable zj equals 0, all the information of xj is already contained in xg, and xj is a redundant predictor, collinear with xg. The codec is also used to measure conditionally independent predictors. Given a subset S of relevant predictors, if Tn, y, xj, xs, is close to 0 for a predictor xj, xj can be considered a conditionally independent predictor. The TNVS approach involves a three-step heuristic search to categorize predictors into the mentioned subsets. A flowchart illustrating the proposed TNVS is provided in Figure 2. The approach begins by identifying and removing uninformative predictors based on Shannon entropy. Next, it identifies and removes redundant predictors using GSO. Finally, it identifies and removes conditionally independent predictors using the codec. The indices of the selected predictors are reserved in the relevant subset S, while those of the removed predictors are categorized into the uninformative subset A1, redundant subset A2, and conditionally independent subset A3. Here is a combined summary of pages 7 and 8. The proposed TNVS, transparent nonlinear variable selection, algorithm is a heuristic search method for variable selection in regression analysis. It consists of three steps: prefiltering, forward selection, and batch deletion. In the prefiltering step, uninformative predictors are identified and removed using an uninformative score, UINS, based on Shannon entropy. The forward selection step identifies the most relevant predictor to the response given the current relevant subset S, using a relevance score, RELS, based on the codec measure. The batch deletion step identifies multicollinearity in the remaining predictors and removes redundant predictors using a redundancy score, REDS, based on generalized squared orthogonalization, GSO. The TNVS algorithm is outlined in Algorithm 1, which takes as input the predictor matrix X, response vector Y, and three thresholds alpha 1, alpha 2, and alpha 3. The algorithm iterates until the termination criterion is reached, which is either the maximum model size Dmax or the relevance score of all remaining predictors falling below alpha 2. The output is a relevant subset S, an uninformative subset A1, a redundant subset A2, and a conditionally independent subset A3. The computational time of TNVS is O(dn) ln, on average, where d is the number of selected predictors, making it efficient even with limited processors. The main advantages of TNVS are its transparent framework, ability to handle high-dimensional data with complex nonlinear associations, and model-free nature, allowing the selected subset to be used in various learning models. To evaluate the effectiveness and interpretability of TNVS, simulation studies are conducted on three settings of regression problems with monotonic and non-monotonic functional dependence, interactions, uninformative predictors, multicollinearity, and conditionally independent predictors. The results are compared with competitive baselines to demonstrate the validity and conciseness of TNVS. The proposed method, TNVS, is evaluated against 6 representative baselines, including 2 up-to-date model-free and nonlinear methods, 2 classic model-free and nonlinear feature screening methods, and 2 stepwise methods based on linear partial correlation. The parameter settings of the variable selection methods are listed, including the uninformative threshold, relevant threshold, and redundant threshold for TNVS, as well as the termination criterion, significance levels, and number of selected predictors for the other methods. The performance of the methods is evaluated using 10-fold cross-validation on each dataset, with the average result of all folds on all 10 corresponding datasets. The effectiveness and efficiency of TNVS and baselines are evaluated on high-dimensional simulations with complex nonlinear functional dependencies using 4 criteria. PA, the probability of discovering all truly important predictors. M, the minimum model size required to include all true predictors. coverage, the number of true predictors covered by the selected subset, and time, the average running time. The results show that TNVS outperforms the other traditional methods, with a higher PA, smaller m, larger coverage, and less computational time. The framework of TNVS is most similar to that of foci, but TNVS has a smaller minimum model size and a larger coverage, indicating that it is more accurate and reliable than foci. The experiments demonstrate that every module of the proposed TNVS is effective and indispensable. The nonlinear codec ensures that TNVS can effectively identify complex nonlinear associations, and pre-filtering and batch deletion inherently improve the effectiveness and efficiency of TNVS. Finally, the interpretability of the proposed method is demonstrated by evaluating the proportions of truly relevant, uninformative, redundant, and conditionally independent predictors in the selected subset. The results show that TNVS has the largest proportion of truly relevant predictors and the smallest proportions of uninformative, redundant, and conditionally independent predictors, indicating that the selected subset is the most concise. In the context of machine learning and high-dimensional data analysis, the proposed TNVS, tree-based nonlinear variable selection, method demonstrates superior performance in terms of model interpretability and predictive accuracy compared to its baselines, foci and WLS. The TNVS algorithm divides predictors into 4 distinct subsets: relevant, uninformative, redundant, and conditionally independent. This division enables a more nuanced understanding of the relationships between predictors and their impact on the response variable. The evaluation of TNVS is conducted through extensive simulations, which show that TNVS outperforms foci and WLS in both predictive accuracy and model interpretability. Specifically, TNVS achieves a higher recall for relevant predictors while maintaining a lower false positive rate. It also effectively identifies uninformative and redundant predictors, providing a clearer understanding of the predictor-response relationships. To further validate the efficacy of TNVS, 4 real datasets from various domains are utilized, including Arsine, Isolet, Warpart 10P, and ORL. These datasets represent high-dimensional data with potential nonlinear correlations between predictors and responses. They also contain a large number of uninformative, redundant, or conditionally independent predictors, making them ideal for testing the capabilities of TNVS. The results from these experiments demonstrate that TNVS can effectively identify relevant predictors and distinguish them from uninformative, redundant, and conditionally independent predictors. This capability is particularly evident in the Warpart 10P and ORL datasets, where TNVS successfully identifies facial landmarks that are crucial for classification tasks. This indicates that TNVS can provide valuable insights into the underlying mechanisms of complex systems and improve the interpretability of predictive models. In conclusion, the TNVS method offers a promising approach to handling high-dimensional data by providing a comprehensive framework for variable selection. Its ability to differentiate between relevant, uninformative, redundant, and conditionally independent predictors makes it an attractive tool for researchers seeking to enhance model interpretability and predictive accuracy. Here is the combined summary of pages 13 and 14. The proposed tuned nearest variable set, TNVS, method is evaluated on multiple learning models to demonstrate its effectiveness and generality. 5 prevailing predictive models, including support vector regression, SVR, support vector machine, SVM, random forest, RF, decision tree, DT, light gradient boosting machine, light GBM, and multilayer perceptron, MLP, are considered. Each learning model is trained with the selected predictors, and the results are compared to examine the predictive capabilities of these variable selection methods. To evaluate the predictive performance, repeated 10-fold cross-validation is adopted, and the results are evaluated with out-of-sample accuracy, ACC, recall, F1, and the Cohen-Kappa score, kappa. The Friedman test is performed to demonstrate the predictive capability of the proposed TNVS, and the results show that TNVS attains the top 2 among the 7 methods on real datasets, with significant differences among these methods. TNVS transparently groups the predictors into 4 subsets, namely relevant, uninformative, redundant, and conditionally independent, which improves the model interpretability. The average cardinalities of the 4 subsets are counted, and the average compression rate is calculated. The results show that the percentage of relevant predictors is lower than 6% in all datasets, indicating that TNVS compresses the input set of predictors to a large degree. Redundant predictors are identified in all datasets, and uninformative predictors are identified in ArXiv as expected. In addition to model interpretability, the variable selection results of the ORL dataset are visualized to demonstrate post-hoc interpretability of TNVs. The results are intuitionistic, and the selected pixels cover most if not all of the key reference points, providing insight into capturing the key predictors of these observations. In the context of high-dimensional data analysis, the proposed transparent and nonlinear variable selection (TNVS) method is designed to identify relevant predictors and eliminate uninformative, collinear, and conditionally independent predictors. The TNVS algorithm consists of a 3-step heuristic search that first selects predictors relevant to the response, then removes uninformative predictors, and finally deletes collinear and conditionally independent predictors. This method utilizes a recently proposed nonlinear partial correlation measure to detect complex nonlinear functional dependencies between the response and predictors, including monotonic and additive relationships. The performance of TNVS is evaluated on 4 real datasets: ArXiv, Isolet, Warpart10P, and ORL, and compared with 6 baseline methods. The results show that TNVS outperforms the baselines in terms of prediction accuracy and variable selection, with the exception of Warpart10P, where TNVS and WLS achieve similar results. The visualization of the selected pixels on the original images of ORL demonstrates that TNVS accurately detects key facial points, such as eye corners, eyebrow corners, tips of the nose, corners of the mouth, and chins, which are essential for facial discrimination. To further demonstrate the robustness of TNVS, the sensitivity of the method to changes in its 3 thresholds is tested. The results indicate that TNVS is insensitive to changes in the thresholds within certain ranges, with the number of selected predictors fluctuating slightly in response to the change in the thresholds. This suggests that the proposed method can maintain its performance even when the thresholds are adjusted. In conclusion, TNVS provides a robust and efficient approach for variable selection in high-dimensional data, capable of identifying complex nonlinear relationships between predictors and the response. The method is shown to be effective in various datasets and robust against hyperparameter variations. Future work may involve extending TNVS to handle more complex data structures and improving its efficiency for extremely large datasets. The proposed method for variable selection in regression analysis focuses on identifying relevant predictors, removing redundant ones, and identifying conditionally independent predictors. It employs a 3-step heuristic search, including prefiltering, forward selection, and batch deletion. The method utilizes information entropy, Gram-Schmidt orthogonalization, and nonlinear partial correlation to classify predictors into 3 unimportant subsets. The effectiveness and model interpretability are enhanced through this process. However, limitations and potential extensions are acknowledged, such as the use of non-parametric statistical tests for threshold improvement and consideration of domain knowledge for detecting hard-to-identify interactions. The method's efficiency can be further improved by adopting advanced algorithms like genetic algorithms in high-dimensional scenarios. The authors provide a detailed example and results on real datasets to demonstrate the method's capabilities and performance. The provided pages from the research paper detail various machine learning algorithms and their performance on different datasets. Starting with the first page, it presents results from several algorithms including light GBM, MLP, SVM, and random forest, showcasing their F1 scores, recall, and kappa statistics. The data spans across various datasets, highlighting the strengths and weaknesses of each algorithm. Moving on to the second page, the analysis continues with more algorithms, including Warpart10P, MLPACC, and RFACC. The results demonstrate the effectiveness of these algorithms in different contexts, emphasizing their suitability for specific tasks. The data also includes ORLDTACC and ISOLETDTACC, further expanding the scope of the study. Throughout the pages, the focus is on the technical aspects of the algorithms, providing precise metrics and statistical analyses. This comprehensive overview serves as a valuable resource for researchers and practitioners seeking to understand the performance of various machine learning algorithms in different scenarios. The provided pages discuss various aspects of feature selection and variable screening in high-dimensional data. They present a range of methods, including Sure-Independent Screening, CIS, Conditional Sure-Independent Screening, CSIS, and other techniques like the lasso and elastic net for regression. The authors highlight the importance of feature selection in reducing dimensionality and improving model performance. They also emphasize the need for methods that can handle high-dimensional data efficiently. The pages include detailed explanations of mathematical concepts, such as partial correlation, and their applications in feature selection. Additionally, they discuss the use of deep learning models for feature selection and the importance of interpretability in machine learning. The authors also touch upon the topic of variable selection in functional data and the use of genetic algorithms for feature selection. Overall, the pages offer a comprehensive overview of various feature selection methods and their applications in different domains. The research by Zhao et al. 2011 focuses on model-free feature screening for ultra-high dimensional data. It introduces a novel approach to select relevant features without relying on a specific model. The method is based on the idea of using the correlation between each feature and the response variable to identify important features. The authors propose a statistical test to evaluate the significance of each feature, which is then used to rank the features. This approach is particularly useful for high-dimensional data where traditional methods may fail due to the curse of dimensionality. The paper presents theoretical guarantees for the performance of the proposed method and demonstrates its effectiveness through simulations and real data examples. The methodology is designed to be computationally efficient, making it suitable for large datasets. The authors also discuss the limitations of their approach and suggest avenues for future research.